So feel free to interrupt me if you have any questions, comments, suggestions. It'd be really great to hear everyone's thoughts on the project. All right, so a broad area of, let me just get these slides going, there we go. So broadly, a lot of my work is in belief formation and learning and settings where people may not accurately form beliefs. And by accurately form beliefs, I mean that they have, say, a correct model of the world. They exactly know how to interpret different pieces of information, and then they use Bayes' rule to map that into posterior beliefs that then inform how they make decisions. So in classic economic learning settings, we often have settings where individuals are using some sort of information about the world. They're, say, seeing the results of a scientific study, reading the news, talking to friends about their experiences. And they use this information to make decisions, to learn about the world, and also to make predictions. And so if we then look at the literature in psychology and economics, the more empirical literature on learning, we find that there's many ways in different settings in which agents systematically deviate from this, what we call the correct Bayesian approach. They have a correct model, they interpret things accurately, and they use Bayes' rule to form their beliefs. So for example, we've seen evidence for failures of statistical reasoning. People have a really difficult time, say, accounting for correlated information when they're updating and learning. We see cognitive biases such as motivated reasoning. People have a preference or derive direct utility from thinking they're competent or of high ability, and that can then bias how they interpret feedback about themselves. And also it just simply may be, as scientists, we could be really great at Bayes' rule and really great at, sort of making sure we don't have cognitive biases when we're learning about a research question, but it's just really hard to discover the relationship between different unknown states of the world and the information about those states. So in general, we always say as theorists that all models are wrong. We may know our model is wrong, but just not have a sense of how to get to that true model. So as economists, we may say, well, given that a lot of the recent theory on economic decision-making is an environment with uncertainty, as well as some sort of learning component, how should we model these sorts of biases and failures of statistical reasoning in terms of how they come into models to influence what predictions we make about people's decisions? So within economics, there's two broad approaches that have been used to address these types of questions. So in general, we maintain the assumption that agents are expected utility maximizers, just as if they had a correct model, but we relax the assumption that they update their beliefs correctly. One way to do that is the model misspecification approach. And this says that an agent uses a model to interpret the signal. In other words, they have some sort of model or belief about how signals arise or pieces of information arise in different states. And they use that model when they see information. They form beliefs from that model using Bayes' rule, just as someone with a correctly specified model would do, but they're misspecified, or in other words, their model might be wrong. They might misunderstand the relationship between signals and the underlying state. So for example, they might misunderstand how likely it is to see a negative health outcome in different states of the world about sort of the association between, say, smoking and lung cancer. Another approach, and this is coming more from the empirical literature as well as the behavioral theory literature, is what we call the heuristic approach. And you could just imagine writing down an arbitrary function that describes how agents form their beliefs. So you take a signal, you take a prior belief, you write down a function that maps it to the posterior belief. And so this approach is often used in behavioral models where they say take a specific heuristic and write it down. And it's something that you could think about also empirically in terms of showing agents information and asking them what their beliefs are after they see that information. So these are two different approaches to get at the same question of how agents learn when they may not form correct beliefs. And each of these approaches has different advantages and disadvantages. Our goal of this paper is going to be to link these two approaches. So if we think about, well, why would you use the model misspecification approach? What's the advantage of this approach? Well, this approach, it can capture a variety of behavioral biases. There's a large recent literature in economics on model misspecification. It can capture many biases without departing too far from the standard framework. So what I mean by that is you can still have a standard framework. Agents have beliefs about the signal distribution. They update via Bayes' rule, form expectations, so on and so forth, just as they would if they were correctly specified. It's just that their models might be wrong. They might have the wrong beliefs about the distributions. So really, essentially, that's the only change relative to the standard framework, is that you allow these distributions to be subjective. Why is this good? Well, it means that existing methods are easier to adapt to misspecified Bayesians because you can do things like apply solution concepts, form expectations, look at the whole rich tool set we have for analyzing decision-making under uncertainty, and really just sort of relax the assumption that agents have a correct model in all of those settings. Further, it can also provide a foundation for and highlight the limitations of arbitrary heuristics. So it can say, look, here's a heuristic. Can we provide a foundation for it by showing someone's more complete model that would lead to that heuristic? Or can we see what models would connect to that heuristic and use that to show, well, what are some of the drawbacks of this heuristic, or what are some unrealistic features of this particular decision rule you wrote down? So the model specification approach is really a natural way if we wanted to take our existing tool set as economists and just try and incorporate biases and errors in sort of the simplest way possible. What do we know from this approach? Well, this approach goes back to the statistics literature. Burke in 1966 showed that for well-behaved data, sort of some minor conditions in how the data is generated, agents are going to converge to the closest model to the truth in terms of the Kullback-Leibler divergence. This has also been used in a recent set of papers on belief dynamics. People have tried to characterize the asymptotic beliefs and actions in misspecified learning, conditions for convergence to what's called a Burke-Nash equilibrium. There's many recent papers in this area, some of my own work with Danielle, as well as some nice papers by Frikajima Ishii, Friedenberg, Lanzani, Strack. A lot of recent work has tried to look at the long-run implications of agents who learn with misspecified models. So we have a really great tool set for analyzing belief dynamics with this approach. We also have a really nice tool set for solution concepts. So Esponda and Puzo came up with the solution concept of Burke-Nash equilibrium, which generalizes existing solution concepts to the case where agents may be misspecified. And we can apply this to settings in which agents have wrong models and are engaging in some sort of strategic interaction. So as you can see, we have a rich set of tools for analyzing model misspecification in terms of how it impacts long-run learning and strategic interaction. But on the flip side, why would we care about the heuristic approach? Well, this approach connects more easily to the applied and empirical literatures. So conceptually, if we want to think about how agents distort signals, the heuristic is it's a much more natural way to think specifically how an agent is distorting signals. In other words, are they counting the signal twice? Are they miscoding certain signals? They're taking signals that say they're not so smart and coding it as thinking they're smart. We can really map sort of a more conceptual interpretation for the cognitive bias or error into this learning rule in a way that it's really natural to see what the heuristic is actually doing in terms of like cognitively what sort of bias the agent is exhibiting. It's also easier to identify from choice data. So if we just gave agents information and elicited their beliefs about the unknown state after the information, that would elicit the heuristic, but not the full misspecified model. So what do we know from this approach? Here we have much more of a case-by-case set of results. Some common papers that have used this heuristic approach are confirmation bias, where you overinterpret information confirming your current belief and underinterpret information that goes in the opposite direction, over and under reaction in Epstein-North-Sandroni. And these results often take the form of write down a heuristic, derive the asymptotic implications for that heuristic. It's tough to get the general results for learning dynamics like we have in the misspecification approach because each heuristic is so specific. So you can't really derive general results as easily. So we have case-by-case results. We also have case-by-case results for which solution concept to pair with the heuristic. So in general, each heuristic comes with its own solution concept. For example, naive learning and Eister-Raven. These different solution concepts are ones that conceptually make sense for that specific heuristic. So again, case-by-case solution concepts, rather than in the model specification approach, we had the much more general Burke-Nash approach. So here we see, the disadvantage of the heuristic approach is the lack of general results, but the advantage is that we have a lot more of a conceptual interpretation as well as an empirical connection for what the heuristic is doing. So what's the goal of this paper? Our goal is to connect these two approaches, to understand how these two approaches are linked. So our key questions are first, when is it possible to represent the heuristic as a misspecified model and vice versa? In other words, when are the two isomorphic to each other? And given we have this representation, if there are multiple misspecified models that represent a heuristic, which one should a researcher select? So the spoiler alert for question 2 is there are in general, multiple misspecified models. That's what makes the question interesting. And so a big part of this paper is putting conditions on the misspecified model in relation to the true model that will then try and pin down which model is the best model to choose to represent a heuristic, given the specific goals of what the paper that's using that heuristic is trying to capture. All right, so now I'm going to jump into the setup. This is pretty straightforward. I'll talk through the representation result, and then I'll talk through the different cases of pinning down which heuristic to select. So let's look at a simple environment with uncertainty. There's some unknown state of the world, omega 1 through omega n, so it's a finite state space. Agents have some prior belief over the state space, and they observe a signal over the state space. So here, to keep things simple for the talk, we're just going to assume that the signal space is a subset of the real line. In the paper, we can look at more arbitrary signal spaces than that, but the generalization sort of comes with some added technical conditions that don't have a ton of economic intuition, but could be relevant in different settings depending on what sort of information you want to look at. So this signal is distributed according to CDF, state contingent CDF, capital F, which specifies the the probability that signal is less than or equal to S in state omega. We also have a PDF lowercase f of s in state omega. And we're going to assume that the signal measures are mutually absolutely continuous across all states. So this basically rules out signals that are perfectly informative in the sense that the signal arises in some states, but not others. So we can always use Bayes' rule to pin down beliefs given this mutual absolute continuity assumption. One last piece of notation, the unconditional signal distribution is just the average of the state conditional signal distributions taken with respect to the prior across the state space. You can think about this as the the CDF for the signal distribution before the state is realized. So here we're just looking at beliefs and how agents update. So we're not going to embed this in a decision problem. But basically, you can think about why would we care about this sort of environment in economics? Well, agents see a signal, they use it to make some decision, and then their payoff is going to depend on that decision as well as the unknown state. So we'll have a couple examples where we embed our findings in a richer economic problem and show what our representation and show what our conditions can use to tell us about economic decisions that we often look at in economics. All right, so the misspecified model is quite similar to the correctly specified model. The agents believe the signal is distributed according to CDF capital F hat with PDF lowercase f hat in state omega. So essentially they have their model is similar to the correctly specified model. They have a state contingent signal distribution in each state. We use hat to denote the subjective distribution to differentiate it from the true distribution. So the model is this family of state contingent distributions, and it's misspecified if the state contingent distribution in at least one state differs from the true distribution in that state. Again, we can let f hat denote the subjective unconditional signal distribution. Again, the average taken across different states, where here we're just using the average of the subjective distributions in each state rather than the true distributions. So one minor assumption we're going to put on the misspecified model is we assume that the misspecified and true distributions are mutually absolutely continuous in each state. And this basically says that models are such that agents can't create fake signals. They can't come to say, oh, I think there's going to be this signal, even though that signal never actually happens. And it also prevents them from observing signals outside of their subjective support. So let's suppose they had a model where they thought there was only one set of signals, but signals were drawn from a different support. Then we wouldn't really be able to use Bayes' rule, as we do in the misspecified model, to pin down how agents update when they see those signals outside of their support. And so these are sort of pretty standard conditions in the misspecified literature that are just put to sort of have a little regularity on the misspecified model with respect to the true model. Now, agents are Bayesian with respect to their misspecified models, as is the standard in the misspecification literature. They use Bayes' rule to update their beliefs after observing each signal, where here this is just the standard expression for Bayes' rule. All right, in contrast, the setup for the heuristic, a heuristic is just a function, arbitrary function mapping the signal space, script S, and the distribution over the state, the prior belief, to a posterior distribution over the state. So it's a measurable function that's just mapping each signal realization and prior to a posterior. Right, so we let HB denote the heuristic defined by Bayes' rule. As you can see over here, Bayes' rule is a heuristic. It defines one particular way. You can map priors and signals to posteriors. But of course, there are other rules we could write down or other functions we could write down for this type of mapping. And for the talk, again, a simple regularity assumption, we're going to assume that the signal space is such that the Bayesian heuristic, as well as the other heuristics we consider, are injective for each P. In other words, each signal maps to a unique posterior. And this is just to simplify the notation. It's, it's fine to have multiple signals mapping to the same posterior. It just sort of conceptually doesn't add much and makes the notation more challenging to see. So as you can see, this heuristics makes it really straightforward to formulate many biases that we can think of conceptually, as I will show you in the next slide. So some examples of heuristics, let's suppose we're in a world with a binary state, L or R. Here we can completely specify beliefs by just the probability that the state is R. So P will denote that prior. The heuristic denotes the subjective posterior that the state is R after a given signal S. And something like base rate neglect, which is where you neglect the prior when you're forming your posterior belief, would be captured by this heuristic here, where you say you take your updating in what looks like Bayes' rule, but you're just taking your prior and you're raising it to some alpha between 0 and 1. So in other words, you're flattening your prior when you're forming your update. That would be what's known as base rate neglect in the psychology and in behavioral literature. We could also think about something like what's called R partisan bias. So if you slant your information to a particular state, for example, that would be capture something like motivated reasoning, where you slant information towards thinking you're of high ability. And that's simply captured by a heuristic that maps each signal to a belief that let's suppose R is high ability, L is low ability. Then you have a heuristic that maps each signal to a higher belief about being high ability than the Bayesian heuristic would. You can capture something like overconfidence or overreaction, where you say count signals twice. That's captured by this heuristic here, where you raise the signal distribution to some power beta greater than 1. Counting signal twice would just be beta equals 2. Also, a common heuristic was the one underreaction heuristic from Epstein-North-Sandroni, where your belief is some weighted average of the prior belief and the Bayesian update with weight less than 1 on the Bayesian update. So if you were fully Bayesian, your heuristic would be equal to the Bayesian update, but your beliefs are too sticky, you're sort of slanting things towards the prior more than you should. You can also capture confirmation bias. So as you can see, it's really easy to conceptually think of what you want the bias to do and then write down a heuristic that captures it. And so our goal is going to be saying which of these heuristics can be represented by misspecified models. Right. So when can a heuristic be represented by a misspecified model and vice versa? What do I mean by representation? Well, by representation, I mean fixing a prior. A heuristic is represented by a misspecified model, in other words, a family of state contingent signal distributions, if for every signal, an agent who uses Bayes' rule to update their beliefs with respect to the misspecified model forms the same beliefs as that prescribed by the heuristic. So in other words, you can find a model such that when you derive beliefs from Bayes' rule with respect to that model, you're getting to the same posterior belief for each signal as that functional form the heuristic is, as the belief that function the heuristic is specified. The opposite direction, we can say a misspecified model induces a heuristic if the beliefs prescribed by the heuristics are equal to the Bayesian posterior with respect to the misspecified model. So often heuristics are described as non-Bayesian updating. In other words, the Bayesian heuristic is coming from the function that's Bayes' rule. A heuristic that's not using the Bayes' rule function it's called non-Bayesian updating because it's a different function. But as you can see from this representation, it has a connection to Bayes' rule when it can be represented by a misspecified model, because you can use Bayes' rule to get to that posterior belief just with Bayes' rule with respect to a different model. So it's sort of, it doesn't necessarily, it shows, when can these sort of random non-Bayesian functions be represented in a way where we're a bit more disciplined by how agents form beliefs, but their model can be wrong, even though they still form beliefs with Bayes' rule. So it provides a nice connection, again, to a lot of the literature on learning, because Bayes' rule really gives a lot of disciplined to doing things like deriving long-run beliefs. And so if we can work with these misspecified models, we're a lot more disciplined in terms of how we can do our analysis relative to just sort of taking any arbitrary function that results in a set of different beliefs. Okay, so the first result is our representation. It turns out that actually this is quite easy to do. So a heuristic can be represented by a misspecified model at a given prior, if and only if the prior is in the relative anterior of the convex hull of the supportive posterior beliefs. All right, so that's a bit of a mouthful. So let me sort of simplify that. So if you think about what's happening when agents update, let's suppose that we're in a simple world, binary state space, prior is 50-50, and there's two signals, so high or low. And the high signal increases the belief that, say, the state is high, and the low signal decreases the belief. Now, if you just wrote down an arbitrary way in which each signal mapped to some posterior belief, then you wanted to find a model that represented that. Let's suppose your prior is 50-50, that the state's high or low, but the low signal maps to a belief 0.6 and a high signal maps to a belief 0.8. So in other words, regardless of the information you see, your belief that the state is high goes up. Now, there's no way you could represent that as a misspecified model because you can't satisfy the classic Bayesian property that the beliefs are a martingale with respect to the prior. So the expected change in beliefs is just equal to the prior, right? If you start at 0.5 and you either go to 0.6 or 0.8, then regardless of the information you see, your beliefs are going up. And so there's no way you could find a model and use Bayes' rule to have that property. What's the problem? Well, the prior doesn't lie in the convex hull of the posterior. It doesn't lie between 0.6 and 0.8. And that's what this condition here is in the simple binary setting, is just that the prior lies between 0.6 and 0.8. So if your posterior goes to 0.6 or 0.8, then the support of your posterior is 0.6 or 0.8. Convex hull of that is the line between 0.6 and 0.8. You need your prior to lie in that convex hull in order for you to be able to find a misspecified model that arrives via Bayes' rule at those two different posterior beliefs. Things are a little more complicated when you go to a non-binary state space or have a richer signal space. So that's why we need this sort of richer condition to account for the richer state space. But largely speaking, you need the prior belief to lie in the middle of the set of posterior beliefs so that you can satisfy the property, this martingale property from Bayesian updating. So this is a pretty mild condition. As long as you're not doing something weird, like just, always moving your beliefs in one direction, regardless of information, you're going to be able to find a misspecified model to represent the heuristic. The other direction is actually super simple. Any misspecified model that consists of mutually absolutely continuous distributions induces a heuristic. Why do we need the mutual absolute continuity? Well, we just need to make sure that agents are able to update using Bayes' rule, following the signals they see. So this direction too is just simply Bayes' rule. The first is a little more subtle coming up with this condition, but it's actually a generalization of a result by Shmaya and Yariv with respect to our more general signal space. So what does this result tell us? Well, roughly speaking, almost any heuristic, modulo some sort of really weird heuristics with unrealistic properties, can be represented. So it's easy to find at least one misspecified model to represent the heuristic. But we're more interested in figuring out what that model should be and how it relates to certain properties of the true distribution. So coming to the next slide, this is good news. If you want to be able to use the misspecified model approach for your heuristic, in general, it will be possible to do this. But the bad news is that it's often not unique, the representation. Often there's actually very many misspecified models that will represent a given heuristic. Okay, so the next thing we want to do is construct a representation to see what such a representation might look like. And so if we fix a prior P and a heuristic and some misspecified unconditional distribution f hat, remember this is the average of the state contingent distributions across different signals, then this heuristic can be represented by a misspecified model with unconditional distribution f hat at P if the average of the posterior beliefs with respect to this misspecified distribution are equal to the prior. So this is really like a misspecified Bayes plausibility criteria, essentially also relates to the martingale property of beliefs. if it's possible that that heuristic, taking the average of the posterior beliefs with respect to f hat, equals the prior belief, then that's really the only sort of reality check we need for this representation to work. And so we can have a misspecified model with this unconditional distribution that represents the heuristic. But actually we can say more. So if a representation with f hat exists, if this condition is satisfied, then actually that representation is unique in the sense that it uniquely pins down all of the state conditional distributions as well. So you take an unconditional f hat, as long as it satisfies Bayes plausibility, it can be part of a model that represents the heuristic. But remember, a model specifies the distribution over the signals in each state. And it actually turns out there's not different sets of distributions of the signal in each state that would reduce to the same f hat and also represent that heuristic. So we can uniquely pin down the distributions in each state by this construction right here. So what did we learn from this second result? Well, first of all, we learned that any misspecified unconditional distribution that satisfies this analog of Bayes plausibility with respect to the heuristic can represent this heuristic. So it sort of gives us intuition for the representation. Each unconditional distribution is either incompatible with the heuristic. In other words, it doesn't satisfy Bayes plausibility or pseudo Bayes plausibility, and so it can't be part of the model, or it uniquely determines the entire set of state conditional distributions. So each f hat that can satisfy this condition will then uniquely specify a model that represents that heuristic. But in general, there's a multiplicity of such unconditional distributions, and hence there's going to be a multiplicity of misspecified models that represent the heuristic. We could also do an analogous result if we wanted to say specify the state conditional distribution in one state. If we wanted to say, here's the conditional distribution in state one, we could have an analogous condition like this with respect to the conditional state distribution. And then also, again, that would uniquely pin down the entire model. So this tells us that there's going to be this problem of multiplicity, but once we specify one distribution that's part of the model, then every other distribution will be uniquely pinned down. So a natural question we could ask then.
Sorry, I think there's a question in the chat if you want to have a look at that. I can relay that. It says, when multiple representation exists, is there one that is optimal regarding efficiency, accuracy, or based on certain criteria? For example, minimizing type 1 error or maximizing welfare?
Perfect. So this is actually where the paper is going. So I will say, our natural thing is, if there is this multiplicity, which one should we choose? And that's going to be what the rest of the paper is two natural criteria that relate the model, the misspecified model, to the true distribution that one may think is plausible based on the different criteria, and will have different applications based on the goal of the particular economic setting. So I will be talking about that for the rest of the talk. All right, so the first question you might ask is, well, does this multiplicity matter? Does it matter if there are multiple models representing a heuristic, in the sense that will different models have different properties or make different predictions? So let's just look at a simple setting, binary state space again. Suppose an agent overreacts to signals. So they use this heuristic where they're, say, double counting signals. This is the heuristic I had from the examples, where they put some weight greater than 1 on each signal. So if they were, say, double counting it, that would just correspond to beta is equal to 2. You think about the agent updates each time they see a signal as if they had seen that signal twice. And let's suppose an agent sees a sequence of conditionally IID signals. So this is what we call exogenous information. Information is just arriving. It doesn't depend on the action choices of the agent. It just exogenously arrives. What happens in the long run? So these are the types of learning settings that the statistics literature on model misspecification was thinking about. So from Burke, 1965, we know that if the true state is R, then beliefs are going to converge to the solution to, the beliefs are going to converge to whichever state minimizes the Kullback-Leibler divergence, that's this distance here, that's D, with the subjective model in that state relative to the true model in state R. So we can think about the true model as the distribution of signals generated in state R, since the true state is R. The agents have a model of the signals in state L and a model of the signals in state R. Whichever model generates an empirical frequency of signals closer to this true model in state R is what agents are going to come to believe. So if that happens to be state R for their subjective model, they'll learn the truth. If it happens to be state L, they'll learn the wrong state. So if we look at in this particular example I just presented, what we would see, we want to see, so to minimize this, we'd want to see, compare the distance between the subjective distribution in state L. And can you see the arrow or no? What is it? Okay. You want to see the distribution between the subjective distribution in state L and the true distribution in state R, and compare that to the subjective distribution in state R relative to the true distribution in state R. So writing out this expression, we see that we have a log likelihood ratio of the probability of the signal, the subjective probability of the signal in state R versus L, multiplied by the true probability, put in the bias that is just equal to the true probabilities, or the true PDFs raised to the beta from our expression for the bias. This factors out, and we actually see that we're going to get the same. It's going to be the same as we would see in the in state R. So we're going to get correct learning. This likelihood ratio is going to be a martingale, and so we always get correct learning in the true state. And so here, this bias is just essentially going to affect the variance of beliefs, but not the direction that they converge to. And regardless of which misspecified model we chose to represent this heuristic, this property here would hold, and therefore we would get correct learning. So correct learning independent of the choice of the misspecified model in this example. So you might think, well, maybe it doesn't matter which model we choose, we'll have the same asymptotic prediction. But it turns out this is really just a crucial feature of exogenous information. Once we start looking at economic decisions, so for example, a social learning setting, where say, instead of observing a sequence of signals, a sequence of agents are observing private signals and then publicly choosing actions. And so an agent at time t is learning from a history of actions rather than a history of signals. Here, because the action choice depends on the information at any given time, then this information is what we call endogenous, in the sense that how to interpret an action is going to depend on the sequence of past actions as well as the signal. So if you see the same action in, say, period 1 and period 3, it doesn't necessarily have the same interpretation. What that means is that now the full model, so the state contingent distributions, matter rather than just the ratio of them. So here, just the ratio matter, and the ratio just reduces to the heuristic. Here now the full model matters. And so from other work I have with Daniel, we show that the asymptotics depend on the misspecified model because the agents are forming their beliefs using the full model rather than just the ratio of the two PDFs. And so here we could have the same heuristic, but different models that represent them are going to lead to different asymptotic predictions. All right, so more broadly, when does the multiplicity matter? Well, we have different misspecified models, but exogenous information will see the same asymptotic results. But if we have different misspecified models, we're going to have different asymptotic results when the information is endogenous. In other words, it's coming from, say, a social learning setting. It's coming from an individual learning setting with experimentation. Anything where the information generated depends on prior action choices is going to be a setting where these choice of the model could potentially matter. And by matter, I mean it leads to different asymptotics. It can also matter depending on the bias. So if the magnitude or direction of the bias depends on the prior, again, that would be something where the interpretation of information is varying with the prior, and we could have different asymptotics. What's an example of that? Well, confirmation bias. Maybe the more extreme your beliefs are, the more you weight information that confirms your belief. So your sort of the magnitude of your confirmation bias depends on how much weight you put on one state. So as we can see, the different choice, there's a lot of economic settings where the different choice will matter for asymptotic results. It's also going to matter when we have some sort of two-stage game where there's a decision that depends on the information, but there's also an ex-ante stage where the agent makes a decision before they see the signal. And to make that decision, they need to form expectations over what signals they're going to see in order to make a decision. So this sort of problem, we need to pin down expectations. And for pinning down these expectations, the choice of model matters. And also, again, for applying solution concepts that are not fully pinned down by the heuristic, then again, we're going to need the choice of model will matter. So basically, in a nutshell, if the heuristic fully specifies everything that's decision relevant, as it does in this first case with exogenous information, all that matters is the ratio of the two models, and that's the heuristic, then we're fine. The multiplicity doesn't matter. But in many economic settings, we need more than just the heuristic to fully pin down or identify the model. And in all of those settings, different choices of model that lead to the same heuristic are going to lead to different predictions for learning, for equilibrium, or for dynamic choice when there's an ex-ante choice that's made before signals arrive. Okay, so let's then think about, well, given that most or many of the economic decisions we think about have these sorts of features, which model should we pick to represent a heuristic? We have our nice interpretation of heuristics coming from psychology and empirical work on how agents have biases, but now we want to really embed it in an economic decision problem. We really need to be working with the misspecified model. The heuristic doesn't fully pin things down. So what are two restrictions that we could think about that might lead to desirable properties or a unique representation? Well, one is something that we call introspection proof, which is that even with infinite data, you have come to no reason to doubt your model. So you're not seeing things like violations of the law of large numbers coming from your model. Another is what we call naive consistent forecasting, which is a misspecified agent and a correctly agent had the same forecast over their future beliefs. So I'm going to drill down into each of these a little bit more to make them more precise. But intuitively, both of them are putting restrictions on the relationship between the correctly specified model and the misspecified model to impose structure on the misspecified model. As we know from the construction result, as long as we impose structure on one of the state contingent distributions or the unconditional signal distribution, that's going to pin everything else down. So we really just need to impose restrictions on the relationship between one of those distributions, not the whole set. So that makes things a little bit easier analytically. All right, so what's introspection? Well, a common criticism of the misspecified approach is that if agents see a lot of data, won't they eventually come to realize they're misspecified? You know, if they think that a coin is, say, flipping heads or tails with probability 0.6 versus 0.4, and it's actually 0.5 versus 0.5, they're going to eventually see the long run frequency of head and tails, and they're going to come to think that that model's wrong. So introspection proof essentially restricts attention to models that won't have those sorts of violations, and that a common approach is that you can choose the misspecified model that'll match the empirical frequency of what you see. So this is often the underlying assumption in some of the heuristic models of particular statistical biases. It's similar to causal misperception in Spiegler's work on the omitted variables in Mallet and Samuelson. And so we want to ask, well, is there a misspecified model that would sort of pass any possible statistical test for misspecification? In other words, you wouldn't ever be able to see that your model was violating, that the patterns of data you see was violating your model. All right, so formally the condition is fixing a prior. P, a misspecified model, is introspection proof if for any measurable set of signals, the subjective probability of seeing signals in that set is equal to the true probability of seeing signals in that set. So essentially, you're matching the unconditional empirical frequency of signals, even if you have wrong state conditional distributions once you actually see that signal. So in sort of the interpretation is that even if you observe signal realizations from an infinite IID set of draws of signals and states, you're not going to see empirical frequencies that look out of the ordinary, even though you may update incorrectly once you see that signal. So sort of a really simple example of something that satisfies this is, let's suppose that there's two states, each one's equally likely, and you just completely invert the state conditional distribution. So you think the distribution in state R is the distribution in state L, the distribution in state L is the distribution in state R. So on average, you have a correct belief about the distribution over signals, but conditional on seeing a signal, you're going to update incorrectly because your state conditional distributions are wrong. And that then therefore, of course, will lead to inefficiencies because conditional on seeing a signal, you're not forming correct beliefs, and therefore you're making choices that are not optimally using the information. All right, so our next result is a sufficient condition for, or a necessary and sufficient condition for this representation to exist. Taking a heuristic and a prior and a true model, the heuristic can be represented by an introspection proof misspecified model at that prior, if and only if, here again, we have something that looks like Bayes plausibility, the average of the posterior beliefs with respect to the true conditional signal distribution is equal to the prior. where F denotes the unconditional PDF. And so from here, if this representation exists, then it's unique. And again, we can completely pin down the state conditional distributions and therefore the full model by constructing it with respect to the true distribution and the heuristic. So basically, we're taking our heuristic, we're taking the true distribution, we're showing a condition on the relationship between the heuristic and the true distribution such that we can find such a representation. And then once we can find this representation, we can uniquely pin down the rest of the model from our construction, similar to the previous result. All right, so I guess I have about 10 minutes left. So I wanted to quickly discuss some of the, how to think about this result. And I had an example of it. I'm going to just kind of talk through the example at a high level so I can have a bit of time to spend on the other restriction as well. And then I'll try and open things up for questions in about 10 minutes. So first of all, what can we say from this result? Well, this is actually a really strong condition. So it's really a strong, it's sort of imposing a very strong requirement on the relationship between the heuristic and the true model. It's not easy to satisfy, or it's not going to be satisfied in many cases. So, it's not, there's a lot of heuristics that we may want to think of it, just there is no introspection proof representation. So intuitively, only biases that are very balanced could be made completely undetectable if you're really sort of slanting things in a particular direction, or really sort of counting signals twice or something like that. It's going to be hard to make that something that you can't eventually detect from the empirical frequency of signals. If we had, say, a model with multidimensional signals, that gives us a little bit more leeway in terms of playing around with things. And so it's a little easier to sort of play around with this joint interpretation over multidimensional signals that parse out to a single belief about the state. And what sorts of economic problems might this constraint be natural in? Well, let's suppose there are settings where, say, heuristics are formed endogenously. So we want to think of a heuristic as something that arises from repeated decision-making. Then this might be a natural constraint to impose on the long-run heuristic, because, if you're sort of forming a model to, trying to figure out a way to update your beliefs, and you're sort of calling it into question and revising it, these heuristics are something that could sort of survive, infinite iterations of this sort of revision process of trying to settle on a heuristic when you're looking at data to try and refute your heuristic. What do we see from this? Well, extreme heuristics are costly in the sense that any misperception must be balanced out. So if you're, say, trying to, have some sort of self-image concern where you think you're the high type, then you can't just sort of go all the way to interpreting everything as thinking you're the high type, because you're going to have to sort of keep these probabilities of each signal in each state equal to the true distribution. And so this can be thought of as, when agents are iterating and sort of being scientific about how they're updating their beliefs, then this is going to put a bound on the magnitude of a bias that can arise. So we have a simple example. So here we just show that the heuristic for underreaction by FC North Sandroni can always be made introspection proof, whereas other versions of underreaction are more difficult to. And so if we wanted to, say, apply this to a motivated reasoning problem, I'm not going to go through this example in detail in the interest of time, but just to talk through what we learned from this, let's suppose we had a model of endogenous belief formation with self-image concerns. So we had a dual selves model where someone was trying to make a decision that depended on the state in period 2, but also cared about their belief that they were the high type. And the period 1 self is sort of choosing a heuristic that the period 2 self will use, trading off the utility or the payoff that the period 2 self gets from thinking they're the high type with the accuracy of their decision that they need to make given their belief about the state to take some action in period 2. And so we wanted to think about, well, how should we sort of constrain the heuristics that this period 1 self can choose, given that they care both about their self-image, so thinking they're the high type, as well as a more accurate belief about their ability is going to lead to more accurate decisions in the second period. A natural constraint to impose would be that the managers or the period 1 self is selecting a heuristic that's introspection proof, because that means that the period 2 self is never going to come to doubt the way that they're updating their beliefs if they, say, sort of question at each period if they're making repeated decisions. And so we show here that we can actually, in this simple setting, we can characterize the optimal heuristic, and we show that it puts a bound on the degree of the bias the agent can have coming from this motivated reasoning or preference over caring about their type. In other words, they can't just sort of map everything into thinking they're the high type. And so a natural takeaway is that introspection proofness is going to discipline the magnitude of biases in behavioral setting. It's going to force people to misperceive signals in a way that maintains some connection with the true distribution and doesn't let them push information all the way to an extreme. And so compared to the optimal heuristic that would emerge in this dual cells model without the introspection proof constraint, agents are going to exhibit less bias in the long run. They're going to come to have a heuristic that has less bias relative to the unconstrained problem. So this is a natural approach that we can use if we want to think about these dual cells model where the bias serves some sort of purpose. It helps agents with their self-image, but it also has a negative effect by reducing the accuracy of their decisions. Trading these off, it's a natural way to put a constraint on behavioral models. Biases can emerge. We can have biases emerge in this sort of choosing the optimal heuristic setting, but huge biases will be unrealistic. Okay, so in the last 5 minutes, let me talk about the other constraint we may wish to put on selecting the misspecified model. As I mentioned, another drawback of heuristics is that they don't pin down an agent's forecast about their future beliefs. And so if we looked at a simple problem where, say, at time 0, an agent is going to choose whether or not to take a line of credit for some price C, and then at time 1, they have some uncertain income realized, let's say either high or low, or they generate income by 1, and then at time 2, they have some uncertain income realized, and they choose whether to borrow in period 1 based on some signal of what their future income would be. So the important thing in this setting is that agents need to make a decision about taking out the line of credit before they see the signal that's going to inform their borrowing decision. And so in order to analyze this, we need agents to be able to form expectations about what signal they will see. And that's something that's not pinned down by the heuristic, which is the heuristic is going to say how each signal maps into a belief about period 2 income. Okay, so here, a natural way we may wish to pin this down is say that the agent naively forecasts that they'll behave as if they were correctly specified. In other words, when they're forming their beliefs, they think the probability of their posterior belief being equal to a certain value under their subjective model is the same probability of Bayesian assigns to the belief taking on that value under the true model. So it's sort of this ex ante consistency between a Bayesian's forecast of their beliefs and a misspecified model, a misspecified agent's forecast of their beliefs. All right, so what's the formal definition of this? Well, a misspecified model representing a heuristic exhibits what we call naive consistent forecasting if for all potential sets of posterior beliefs, the probability that the posterior belief is in that set, the subjective posterior, is equal to the true posterior that the Bayesian, the true probability that the Bayesian posterior is in that set, where the subjective posterior is formed from the model and the true posterior is formed from the true model. So it's a form of prospective reasoning. The agent believes that they'll form each posterior at exactly the same frequency as a correctly specified agent would, but after observing that information, they actually form their posteriors differently. All right, so what sorts of properties do we need to construct this type of representation? Well, clearly the set of subjective posteriors needs to be equal to the set of Bayesian posteriors. Otherwise, we can't have the same probabilities over them if the supports are different. But it actually turns out that modulo some minor measurability constraints in order for things to be well defined, that this is just about sufficient for the condition. So we assume that we also need to assume the heuristic is null set preserving in the sense that measurable sets under the heuristic are equivalent to measurable sets under the Bayesian heuristic. So given this, again, our result is that fixed a prior in a heuristic, a misspecified model that exhibits naive consistent forecasting and represents the heuristic exists if H is null set preserving. So really these mild conditions for existence. And then if such a model exists, again, we can construct it for all measurable sets of signals. The subjective posterior of that set is just equal to the relationship between the Bayesian heuristic and the true heuristic. So this is a construction that tells us what that model must be. So what's an example? Well, something like partisan bias, where you're just essentially slanting information in one direction. It's really easy to write down a misspecified model that satisfies naive consistent forecasting and represents this heuristic. All right, so what do we learn from this? Well, this is actually a much more general condition for representation than the introspection proof. In general, most heuristics can be represented by a naive consistent forecasting misspecified model. So it's it's a lot easier to find these sorts of representations. It's a lot weaker of a condition than the introspection proof condition. It's an easy condition to check, and it's, again, from our result, we have a construction of the model that satisfies this. So it's straightforward to take a heuristic, take the true model, and use that to then construct the misspecified model that represents that heuristic and gives this particular property. Another thing that I don't have a ton of time to talk about, but it can alternatively be justified as a form of introspection proofness with respect to social information. So something like the social learning setting, where your beliefs about what other people are seeing need to be introspection proof. This naive consistent forecasting also has that sort of interpretation in social learning settings. And so coming back to the credit example, what can we use this type of representation to learn in an economic decision-making problem? Well, suppose the agent has a heuristic that slants her beliefs towards high income. So she's overly optimistic that her income is going to be high in the final period. And let's suppose this heuristic is null set preserving. So then we know a naive consistent forecasting representation exists. And we also have the result that in the ex ante decision, so when the agent is using this misspecified representation to form expectations, the misspecified agent is going to accept or take out a line of credit and be willing to pay C, or the price for that line of credit, if and only if the correctly specified agent does. So it's naive consistency. So in other words, in the first stage, the misspecified agent and the correctly specified agents have exactly the same willingness to pay for credit. But then in the second stage, the misspecified agent, because they were naive in how they form their beliefs, once they actually see the signal, they're going to borrow more. And so if we wanted to say, look at a standard contract design problem with this sort of bias, if we started with a heuristic, we'd need this model to pin down the rest of the problem in order to analyze it. And if we wanted to think, well, how would this sort of representation impact contract design? Well, because when they're making forecasts, the naive agent and the naive consistent agent and the correctly specified agent make the same forecasts or have the same beliefs over their forecasts, you can't do ex ante screening on entry into the credit card contract. So they're both willing to pay the same price. You can't have contracts that price discriminate on accepting credit, but you can then charge different interest rates. And so here, the same price would be optimal for the correctly specified and naive agent, but the credit issuer, the contract design would be such that they then charge more for borrowing, given that the naive consistent agent over borrows once they actually accept that credit. Whereas without this naive consistent forecasting pinning down the unique model, if we wanted to analyze this type of setting about how should we do contract design when we have an agent who's overly optimistic about their period 2 income and decides whether or not to take out credit before they observe the signal. So we have that heuristic. We want to then say, well, let's pin down the rest of the misspecified model so that we can analyze this. Without the naive consistent forecasting constraint, we could just construct a bunch of different misspecified models that would capture the same heuristic, and they would also have very different comparative statics in terms of how the optimal choice of the price of credit and the borrowing rate would depend on the agent's decision making. So we wouldn't really even qualitatively be able to uniquely pin down what the optimal contract would look like just from the heuristic. We could get lots of different results depending on our choice if we didn't flesh things out with this constraint on the misspecified model. All right, so let me wrap up since I only have a couple of minutes left. What do we learn from this? Well, many heuristics can be representative misspecified models. This is good news. We can use off-the-shelf results from the misspecified literature, which are a quite general set of results in order to analyze how specific heuristics and biases impact things like learning or decision-making. So it fills in the gaps left by the heuristic in the sense that it lets us fully specify a model to do strategic analysis, long-run dynamics, and that sort of thing. But the bad news is that there's too much flexibility in modeling because of this multiplicity, that the multiplicity does matter in many of the types of economic environments we're interested in. So there's no one-size-fits-all approach to representations. There's a variety of different restrictions on the relationship between the misspecified model and the true model that may seem appropriate depending on the context. We introduced two interesting classes of misspecified models. naive consistency, which is relevant for how agents form forecasts in an ex-ante decision-making stage before information arrives. Introspection proof, which is more of a retrospective condition, how agents look back at their decision-making versus the actual frequencies of information they saw and whether or not they would ever come to question their model. A couple other things we look at in the paper that I don't have time to talk about today. Introspection proof, as I said, was a really strong condition. So we could think about weakening a bit what we call alpha introspection proof, as long as what you see is sort of within a certain set, or within a certain alpha parameter of what you would expect to see. So as long as you're close enough to the true model, even if you're not exactly observing empirical frequencies that are exactly equal to it. And then conditional introspection proof, which is essentially our introspection proof condition was applied to the unconditional signal distribution. If you were, say, looking at a learning setting where the state was fixed, you may wish to instead apply that condition to one of the state conditional distributions, so the true state. And so we could also do the same sort of analysis, saying fix a state at the beginning, and the agent's model needs to be introspection proof with respect to the distribution of signals in that particular state. So I'll stop here, and happy to take any questions or comments, or go back and clarify anything that wasn't clear.
Perfect. So thank you so much. So again, I would just invite whoever has question to just really unmute yourself and ask directly, or write it in the chat, and then I can relay the question. Maybe just to get things rolling, I will start with a question of my own. So one thing, if I understood correctly, like when you want to create the misspecified model, you basically create a different model per each prior. Like, so basically depending on the prior that the agent has, I'm going to create a different model. Is that correct?
Yeah, so great question. So I didn't have time to get into the details on that, but if we come back here, the representation. So in general, the misspecified model can depend on the prior P, but in the paper, we have conditions for which the misspecified model is independent of P. So in other words, the same misspecified model represents a heuristic at all priors, right? Because the misspecified model is not necessarily, the misspecified model is just state contingent signal distributions. The heuristic is mapping each prior signal into a posterior. And as long as the necessary and sufficient condition is what exactly that signal distortion looks like. So if the signal distortion doesn't depend on the prior, then there's a prior free representation. By prior free representation, I mean that there exists a misspecified model that represents the heuristic at all priors. So let's come back to the heuristic examples. Here you can see something like overconfidence or overreaction, so counting signals twice. This distortion doesn't depend on the prior. The prior enters in the same way, and the distortion is purely coming on the true signal distribution. So there would be a prior free representation for that. Whereas something like this base rate neglect, here the distortion depends on the prior, and so that would be something where there's not a prior free representation. Or also something like confirmation bias. So confirmation bias is, let's suppose you're in a binary state. If your belief that the state is L is above 1/2, you slant information towards state L relative to the true belief. If you believe that the state R is more likely, you slant information towards state R. Then clearly that bias depends on the prior. And so clear that the misspecified model would also have to depend on the prior, because for one set of priors, you're slanting beliefs in one direction, and for another set of priors, you're slanting beliefs in a different direction. So it depends on the bias whether or not you can have a prior free representation.
Perfect. Is there any question from the audience? I can ask you another question in the meantime that I was thinking about. So I guess like in this setting, you know the heuristic, right? And you want to create the misspecified model. I was wondering, and this is, I mean, maybe that I don't know enough the area, but like, is there a way to just get through either one of these just from data? Like if I observe an agent making decision, is there a way that I can reconstruct either what the heuristic was or directly what a misspecified model is that kind of justifies the action that I see the agent taking?
Yeah, so that's a great question. So, we're presenting this as like going in both directions, but really way I think of it is the heuristic is what's generally identified from data. You know, if you think about experimental data trying to study biases, or even real world data where there's some sort of eliciting beliefs, if you say if your treatment is different pieces of information, so you're giving different groups of people different pieces of information, and then you're eliciting their beliefs, that will give you the heuristic. You know, if you say know their prior belief, give them a piece of information, and then ask them what their posterior belief is. So any empirical paper that elicits beliefs will give you the heuristic. Mm-hmm. So the heuristic is really what I view as the approach that's used in the empirical literature studying biases and belief updating. And it's also the approach that's used conceptually when thinking about psychology. Whereas the misspecified model approach is the approach that's used in the game theoretic and also microtheory, like learning literature, in terms of thinking about, let's write down a general model and analyze the long-run properties of it, or let's write down a general model and analyze a solution concept for it. And so the advantage of one of the advantages of the heuristic approach is that's the connection with a lot of empirical work. Mm-hmm. But as I said, the disadvantage is that it doesn't fully specify doesn't fully pin down the model that's necessary for analyzing economic decision problems with either social or endogenous information. And so the misspecified model approach is where you have a lot of the meat for those types, a lot of the results and tools for those types of questions. And so this connection is essentially connecting the two. Mm-hmm. Right. So you can think about pin down the heuristic from data, and then you want to know, but now you need a representation in terms of a specified model to make predictions in a theoretical model. And that's when you want to know, because of this multiplicity, which one should you pick? Which model should you pick to represent that?
That's wonderful. Perfect. And I see there is a question in the chat, so I can read that. So just as one heuristic can be represented by multiple misspecified models, can the same misspecified model get manifested as multiple different heuristics?
No, I mean, in general, the direction of misspecified model to heuristic is just simply Bayes' rule. Like you can think about the heuristic from a misspecified model is just, let me just scroll back for a minute. Right, so you take a misspecified model, here's the setup for the misspecified model, your posterior belief is just Bayes' rule with respect to that misspecified model, and that's exactly the heuristic. It's the Bayesian heuristic with respect to the misspecified model. So this is pinning down the posterior beliefs. And the intuition is that the misspecified model is fully describing the decision environment, whereas the heuristic is not fully pinning down the decision environment. So that's why you have the multiplicity in one direction, but not the other.
Okay. So if there's no other pressing question, I think...
Can I also...
Oh, sure, go.
Well, I actually have two questions. This is a great talk and very fascinating. One is regarding agents in large populations. So suppose, so because there's a value in wisdom of crowd, and people may have repetitive learning from each other, and then eventually the heuristics of diverse heuristics from the population may allow the agents eventually to collectively learn the true state of growth, or is there any way that a convergence result, which your opinion about on this people having divergent misspecified models, and then eventually is there a way to see that they may converge? And second question is, take a well-studied, well-critiqued model in, say, Fama-French three-factor model or Taylor rule in monetary policy. Is there a way to come up with a criterion how misspecified these models are, or what kind of heuristics could these models represent? Yeah, thanks.
Okay, so let me answer your first question. So, so your first question is looking at, say, if there's heterogeneity, model heterogeneity in the population, and you know, what sort of long run implications might there be? And so, you know, I think that sort of that would really depend on the different settings. So you could imagine something like motivated reasoning. In general, motivated reasoning is a bias that people exhibit with respect to information about themselves, but not others. So like I care about thinking I'm high ability, but I don't have this bias, and I'm trying to evaluate somebody else's ability. And so that would be plausible, the conceptual nature of that bias would be plausibly something that could survive in the long run, because, agents are not, agents are learning differently about themselves versus others. They have this different, and you could think about it as something that, agents it's just sort of like a cognitive error that you just, you can't see your own flaws as well as you can see somebody else's flaws. And so that's the sort of the underlying motivation from psychology for that bias would be something that we would imagine, it's not, people could improve how they learn about themselves, but they're always going to have this sort of optimism towards information about themselves relative to information about others. But I think, we don't really look at long run population questions, but I think it, it could be really interesting to see and ask these sorts of questions about agents with heterogeneous levels of bias, like what would survive versus what wouldn't. I touched on that a little bit on my other work with Daniel, where we look at, sort of a somewhat different question, but we look at, say, often in the behavioral literature, all agents have the same level of a bias, and the asymptotic results are derived with respect to everyone having common knowledge of the same bias. And so what happens if there's heterogeneity? When do the results about an average level of bias equal, say, when are the sort of long run results from an average level of bias equal to a model with heterogeneity that has that average level of bias? So sort of looking at these model heterogeneity impacts. And I think, sort of another natural question you could ask would be, if there is this sort of heterogeneity and people do have, I guess maybe slightly different signal distributions, like what would survive in the long run versus what wasn't. So I think that's a super interesting question. We don't look at it here, but I think that would be, a natural thing to start thinking about in these types of frameworks. And then your second question is taking a specific, just let me know if I'm not interpreting your question correctly, but taking a specific rule, which we could think of, that economists use, say, which we can think of as a misspecified model, can we measure how wrong it is? And I think that sort of relates to the introspection proofness, in the sense that it would really depend on what information you could observe. So something that's introspection proof, you can't ever figure out it's wrong from just seeing the empirical frequency of signals, because it's exactly matching the empirical frequency. And so then you could start thinking about, well, like, what other tests, if you could start, seeing the state as well, and then seeing the empirical frequency in each state, would that help you figure out a violation? That question sort of relates to, again, not this paper, but some of my other work, where we look at robustness. And the robustness questions in this literature are, take a model that's different from the truth, how robust are the predictions of the true model to misspecification? And so in the work that Daniel and I have, we show a set of conditions that show that the correctly specified model is robust, and that you can have a set of nearby models and you get to the same predictions. So a little bit of misspecification doesn't cause too much harm. But there's other papers that show in different environments. So for example, there's a Frikajima Ishii paper that shows that actually even a little bit of bias can induce very different long-run beliefs in other settings. So it depends on the informational environment, whether you have these robustness properties relative to the correctly specified model. So again, a nice question to ask. There are settings where, let's suppose that the true model is really complicated, and so the reason that you're not writing down the true model is because there's, let's say, 100 variables that influence some prediction, but really there's two primary variables that help you predict with 98% accuracy, and then there's 98 variables that each add like a little bit more to that prediction. So something like, macroeconomic forecasting, there's hundreds and hundreds of variables you could consider, but maybe some are lead to more accurate forecasts when the others are omitted versus vice versa. How accurate can you be with those forecasts if you have some sort of omitted variable bias? And depending on the informational environment, you can be quite accurate if you satisfy the conditions for robustness. Whereas if you don't, then then you'll be in a setting where you just omitting, even if a variable has a very small impact on forecasting, it still could lead to a big error. So again, both of those are, I think, great questions for asking in the broader misspecification literature, robustness and long-run population beliefs.
Thank you very much.
Okay, perfect. So I guess it's time to thank our speaker. Thank you so much for a great talk. And thank you so much for all the audience for joining in. And well, we'll see you in 2 weeks, I guess. Perfect.
All right, thank you for hosting me and thank you for coming.